So hello everyone, I'm Chris. I'm going to today tell you a little bit about my research, which is, covering the area of gravitational wave astronomy. And I expect, having met Vicky and been involved in CIERA activities before, you will know something about gravitational waves. I think that's pretty cool, so I'm going to go through and point out some of the things I've been particularly involved in. So astronomy, I think, can claim to be the oldest science. As long as we've been able to look at the night sky, we've been wondering what's out there. Here's a quite beautiful picture actually from back in my part of the world in the UK, just to show that occasionally the skies are clear back in Britain. This is quite rare. This is actually a photo taken by an amateur astronomer who used to help us out with our public events at the University of Birmingham. It's a beautiful, beautiful time-lapse picture. So just using your eyes, you can figure out quite a lot about the universe. You can figure out different things out there. There are planets which wander backwards and forwards. There are stars which seem to stay where they are. There are comets which appear and disappear. And the fact that it's dark, in fact, if you think about it, can actually tell you that the universe had a beginning. Quite profound things you could do with just your eyes. Now, we got to the Renaissance. People built telescopes. It enlarged what we could see with our eyes. So we discovered the moons around Jupiter. We discovered that some of these dots were actually galaxies. We built bigger and bigger telescopes. As we were just talking about, the Dearborn was the biggest telescope in the world at its time, and each time we looked further, we probably saw more detail, we made new discoveries. Now, at the turn of the 20th century, we opened our eyes even further. So instead of just looking at optical light, we expanded across the entire electromagnetic spectrum. So here's a wonderful compilation from NASA of the galactic plane, so the Milky Way, as seen in different wavelengths. So here's optical light. Optical light. Oh, it's this amazing device. You can see the plane of the galaxy here, and you have these dark bands which are dust. So these obscure the stars behind it. But if you were to look in the infrared, you can now see either through the dust, or in fact you see the dust itself. So what was previously something that got in the way is now something which you can study in detail and discover the properties. So each time we look in a different part of the electromagnetic spectrum, we discover something new. We either see the same thing in a different way, we reveal things which were previously invisible, so up into the radio, we see here all the gas which you can't see with the optical, but the structure here is now revealed. And sometimes we make discoveries of things that we didn't know existed at all. So in the radio, we famously discovered pulsars, these highly regular repeating signals that came from neutron stars. In gamma rays, we discovered gamma ray bursts, these extremely bright explosions that we didn't know where they came from. And you can see also in X-ray, we have these bright point sources, these little blobs, which you wouldn't know were there just looking in the optical, but they are the obvious thing in the X-ray. So each time we looked in a new way, we discovered new things, we got a better view of our universe. So now, what can we do about things which are dark, things which don't interact with light at all, or interact very weakly? How can we see more of the universe when there's nothing to see? And of course, the answer is with gravitational waves. So gravitational waves are produced whenever you have something moving. So if you just wave your arms around, you are producing gravitational waves, little ripples in the gravitational field. But those aren't going to be anything which you can detect. To make a worthwhile signal, you see something really dense moving really fast. So really the best source for these are when you have a couple of black holes orbiting close to each other. When you get two black holes really close, they can be moving at a significant fraction of the speed of light. By virtue of being a black hole, they are as dense as you can be. So these are the perfect gravitational wave sources. The question is, or rather was, do these sources exist? So we know that you can get these very dense objects, in theory, from stars coming to the end of their lives. Here's a little diagram showing a simplified picture of what happens to a star based on how big it is. I don't really want to focus on the details here, I just want to impress on you that it's kind of complicated. If you have a low mass star, it's pretty simple. It basically does nothing. It lives its life. A brown dwarf, perhaps. Smaller stars end up as white dwarfs, so something like our sun will, as it gets older, puff up. This happens to many of us. I think we get towards middle age, we get a bit fluffier around the middle. Eventually, though, the core collapses down, forms a white dwarf, the outer layers get blown up in these beautiful planetary nebulae. For more massive stars than this, though, you get something which will collapse down in the core, either to a neutron star, a big ball of nuclear density material, really strange stuff, around about 14 kilometers in radius or so, but still weighing about 1.5 times the mass of our sun. Or the best case scenario for me is a black hole. So this is where the core is so big, so dense that when it starts collapsing down, there's no force which can stop it from collapsing. So there's no material strong enough to withhold the gravity, and it just sucks itself up into a ball of nothing. Basically, you just have left behind twisted up space and time. That's this remnant of its strong gravity. And so here we have the very dense objects.
So each of the rows is a function of the density or size or both?
So this is really the mass.
And mass.
Yes, so that the mass then sets how big it is, how long it lives, and how dense the remnant is.
Okay.
So this is for a star living on its own. If you now have two stars living together in a binary or a higher multiple, the majority of stars, in fact, live their lives in a binary or triple system or quadruple. So our sun is actually quite unusual, living its life alone.
Mm-hmm.
So we know that there are these binary stars out there, and then if they evolve and they're massive enough, they should leave behind black holes and neutron stars, which then can orbit each other and end up as gravitational wave sources. Now, if you have two stars living together, this picture gets much more complicated, because then you can have stars transfer mass between each other. When one explodes, it collapses down, that affects the orbit, and there are all sorts of complicated things that we don't fully understand yet. But that's one of the things we could hopefully learn in the future from looking at what's left behind. So we have some understanding of the properties of these systems already. If you remember, we have these bright sources in the X-ray. These are black holes in a binary system. You have a black hole, you have its companion star. Companion star's coming towards the end of its life, it puffs up. The outer layers then get stripped off, swirl around the black hole, heat up, and that's what we're seeing as this bright pulses here. So we know that some of these exist already. We hypothesized that the gamma ray bursts we talked about are coming from colliding neutron stars, so neutron stars and binaries mushing together and exploding. And the pulsars in the radio, we think, come from these rotating neutron stars. So we know that these things are out there to varying degrees of confidence, but we're not entirely sure of all their properties. They're quite hard to observe. There's no way we could see these black holes if it wasn't for their companion star accreting some. So by using gravitational waves, we can hopefully get a better picture of them, really dig into the details of how these systems form, how many are out there, and how they end up the way they are. Now, so if we want to detect the gravitational waves, the traditional way we talk about them as ripples in space-time, which I think sounds very poetic, but doesn't really tell you what that means. So a passing gravitational wave is a stretching and squeezing of space. So more conventionally, we just talk about the stretching and squeezing of space. So if we have a gravitational wave either coming out of the board or coming in, we get this stretching and squeezing pattern, something like this. So have two polarizations we talk about being called plus, the one that goes up and down, and cross the one side to side. This is, of course, famously imaginative when it comes to names. So we have two polarizations, and we want to look for this stretching and squeezing pattern. The way you do that is you are a little point, and you compare with your friend on the other side and see if they're getting further away and closer to you. You wouldn't know if a gravitational wave was passing on your own. It's only by comparing notes with your friends that you realise that there's space between you stretching and squeezing. Now, you might be able to guess that gravitational waves, at least by the time they've travelled across the universe to Earth, aren't this big. We would have noticed this in our daily lives, if this type of thing was happening. What we are looking for traditionally is something like a stretching and squeezing of 1 part in 10 to the 21. That's a big signal. So the numbers I like to talk about there is we're looking for stretching and squeezing that's the same as measuring the distance between the Earth and the Sun to the diameter of a hydrogen atom, or the distance from here to Alpha Centauri, our nearest neighbouring star, to the width of a human hair. Now, apparently this is quite difficult. I'm not an experimentalist, but they tell me it's very, very difficult. It's taken around about 40 years of development to build the devices that can do this. And this, going the wrong way, this is one of them now. This is LIGO in Livingston. It's 4 kilometre long arms that we are measuring the stretching and squeezing across. So we have the centre here where we combine the signals, we bounce the laser all the way up this arm, all the way back, and then this arm down here, which goes off shot, and back. And we time how long it takes for the light to go down the 2 arms and come back and look for the difference between them. And doing that, you can tell that there's been some stretching and squeezing between the 2 mirrors at the ends, and thus figure out if there's a gravity. These are really, really impressively large instruments. You can maybe just make out the cars in the car park there. This gives you a size of scale of this instrument. It's really, really impressive. So we now have a network of these detectors across the world. We of course have the 2 LIGO detectors at Livingston, as we just saw. We have Hanford in Washington State. These started operating in their advanced configuration in 2015, September 2015. That was our first observing run, that's lasted around about 4 months. Took them offline, we upgraded them. We started observing again in 2016, around about November time, for our second observing run, O2. I've warned you that this is very imaginative when it comes to names, so O1, O2, and at the end of O2, we were joined by Virgo, which is the French, Italian, other European detector, based in Italy, just outside Pisa. It's 3 kilometres long instead of 4 kilometres long, but otherwise quite comparable to LIGO. I guess I should put in a mention that there's another detector, which is probably still running as we speak right now. This is GEO 600. It's a British-German instrument. It's only 600 metres long, hence the name, again, very imaginative. So it's not as sensitive as the other instruments, but it is particularly useful because that's where we test a lot of the new technology before putting it on the bigger detectors. Some particular cool method for improving the sensitivity called squeezing being demonstrated there. That's going to be put over to the LIGO detectors for O3, which you might be able to guess is our 3rd observing run. This is due to start at the beginning of next year, probably. Okay, so those are the ones currently operating. In addition to that, we have another detector currently being built underground in Japan. This is CIERA. This is quite an exciting instrument by virtue of being underground. It's in a disused mine where they stopped mining stuff and now they do science. So there's a big neutrino detector down there, so they detect these incredibly hard to find subatomic particles. Big vat of water, basically. They look for flashes, they have that down there, and now they can get a gravitational wave detector. Being underground is a good thing because it shields them from a lot of vibrations, which are a source of noise for the detectors.
Is that why it's underground? I mean,
Yeah.
So was that ever thought of with the other detectors? I mean,
Yes.
Were they?
So
Yeah, go ahead.
it's going underground is expensive, so it costs a lot of money digging the tunnels, doing the infrastructure. So I don't think it would be done if they didn't already have this mined location where they basically had one of the arms already built. And so they need
How long are the arms at CIERA?
they're, I think it's 3 kilometres. So it's a big thing.
How much does that arm length affect sort of sensitivity?
It does.
Is that a big deal, like the difference between 3 and 4?
Not a big deal between 3 and 4.
But the 600 to 3 or 4 is.
Yeah, so factor of either.
But their low end will be higher, right?
So
The low end of their detection frequency.
yes, so they will get be able to find signals at slightly lower frequencies by virtue of being underground, because one of the things that limits our low frequency sensitivity is the vibrations, and they are shielded from that.
This is why Lisa will be so good at that, because,
Oh, you're spoiling everything.
oh, sorry.
Is Lisa the satellite?
We'll find out later.
Yeah, that's right. You don't have the satellite up there.
Is she one of your grad students?
The other thing that is the next generation of detectors after LIGO, the European version, which we call Einstein telescope, is planned to be underground for exactly these reasons that you're
What's the planned length of the arms of Einstein?
I don't remember. Do you remember? It's longer. It's 10 times longer, right? 40 kilometers.
Well, that would be the Cosmic Explorer.
Oh, that's Cosmic Explorer, right?
Uh,
That's
Einstein is slightly short.
yeah. Okay.
So that's gonna be
Bigger.
Is
underground?
that the third one then too? I mean, so you got another one, or I guess it would be 5 or 6 in the generation, so.
Yeah. Well, what Christopher didn't say is it took 50 years to figure out how to do this, and then
Right.
he said it took 40 years to do the technology for
Right.
LIGO. And so we are projecting ahead. What's this going to look like 100 years in the future? Because developing the technology is going to take
Yeah.
effort.
Building these things
Yeah.
it takes a lot of time.
How far underground are they?
At Kagra, I can't remember. It's under a mountain.
Yeah.
So it's in the
Pretty
Japanese
deep, yeah.
Alps. So that they have a lot of rock above them, but I don't think they're actually that far underground.
Oh, just going through something that
So
is,
they are a bit down, but I'm afraid I don't remember. the
Are they choosing sites because of certain geology? I mean, is there a rock structure or something that minimizes the vibration and?
So yes and no. So the US sites were picked mostly because this is cheap land. So Hanford is in a disused nuclear site, Livingston's basically a swamp. But
All good locations.
on top of that though, they maximise the distance between the sites because the further apart you are, the better you are at locating sources. And then on top of that, they were looking at sites where they could invest in science because there wasn't a lot of science around in those areas. So Louisiana isn't particularly rich in promoting scientific endeavour, but now you have it's wonderful.
Highly
facilities.
scientific.
They do a lot of outreach.
So-
there.
so there was- So there was a senator from Louisiana on the NSF board at some point, and
Yeah.
Maybe, I don't know.
Yeah.
I don't know.
You know how these things get done. Is there a lot of infrastructure in the arms?
No. Well, you need to, building the arms is a big thing because they are vacuum tubes. They are
Yeah,
the biggest
okay.
vacuums we have on the surface of the Earth. They're around about half the expense of building one of these, in
Okay.
fact. But they're very simple once they're built because they're big tube and nothing.
Right.
So if you go to the sites, they have displays on the ground so you can kind of see what the internal workings look like.
Okay.
And so in the picture that Christopher showed of Livingston, where you can see the arm, that's basically a concrete dome that's over the tube. It's about the width of these two tables. And then there's kind of a 1 meter tube inside. And that's all there is. Right?
Cool.
So the Japanese site, as you might expect, is not necessarily a good location because Japan is quite subject to earthquakes.
It's a seismic area.
But being underground actually does help for that. I did a tour of Kagra a couple of years ago, so it was still very much in construction. There was water everywhere. And if you remember, there was a big earthquake on December 26th a few years ago, and the scientist giving us a tour told us about he was down the mine when that happened. And all he knew about it was when he come up and he found he had like 10 missed calls from his mother because she was worried, didn't know a thing had happened. Came up. So being underground definitely helps there.
How far is Kagra away from coming online?
So this will hopefully join us at the end of 03. So
oh wow, that's close.
it will be at a low sensitivity, so it will not be probably sensitive enough to contribute to any detections we make. But this will be extremely useful for us, as in people who analyse the data, to practice getting all the data from the different instruments together, combining it together.
Geo is in Germany?
Yes.
And where in Germany?
It's just outside Hanover. It's in a field. There's an occasional source of noise where people in the field next door start ploughing.
Oh, no.
Have to note that down. And,
With the exception of Kagra, you can see all of these in Google Satellites. So if we can send you the coordinates, you can zoom in and look at it. You can see it's got the farm fields around it and
Oh,
everything.
cool.
So,
That's
yeah.
pretty cool.
So those are the ones sort of in works nearly coming on, and then the final one is LIGO India, which is basically taking another LIGO, which we have lying around, and shipping it out to India where they will assemble it. And they've just started working on a site, in fact. So that will be probably 2024 or so before it's online. But that will, again, add to the network and will be a great boost for Indian science and gravitational wave science in general. So by the middle of this decade, we're probably going to have a worldwide network of 5 detectors, making more detections than we can figure out what to do with in all honesty.
But with that network, will you get ever more precise as to the source?
Yes, so it's...
All of them will play into that.
So it's actually diminishing returns in what you can learn about a signal when you add more detectors. So the difference between having 4 detectors and 5 detectors is not a big difference. The big difference really is going from 2 to 3. Now, one of the things which people often don't appreciate is by having more detectors, it makes a big difference because the fraction of time which you have at least 3 detectors online goes up. You can't run these all the time. They're difficult instruments, they take maintenance. Occasionally there are things which occur which take them offline, so there might be a big storm or an earthquake or something like that, they go down. And when you do that, that makes a difference. So when you have 5 online, there's a huge fraction of time when you at least have 3, which means that pretty much any signal that you happen to detect, you will have really detailed information. So that's really the big win you get. Okay, so it's taken us around about 40 years to get to this point. We were planning on switching on our LIGO detectors for the start of 01 on September 14th, 2015, 9 AM. On the Friday beforehand, we decided not everything was actually quite right. We hadn't got everything installed. We're just going to push it back by a week. Unfortunately, the universe did not get the memo, and at 9:52 on September 14th, this happened. This, I think, is still, one of the most beautiful things I've ever seen. This is our first detection of gravitational waves. This is GW 150914. As I've said, this is not the most imaginative when it comes to names. So, GW gravitational wave 2015 September 14th, so GW 150914. We made this detection. Fortunately, the instrument was in a good enough state that we knew it was behaving, and suddenly all that extra maintenance work that people didn't think they could get done, scientists decided on, we'll leave that, that's fine, or you know what, we can do that right now. And it was a massive panic to get this analysed, but we did. And this has opened up this new era of astronomy. So here we have some very nice wiggles. We're measuring here the strain. This is the amount of stretching and squeezing. You can see there's 10 to the minus 21 up here, and you can see that's actually the peak. The instrumentalists are very keen to point out that they can do about a factor of 10 better than that. This is a loud signal. We can measure this with ease. Lasted just about 0.2 seconds. What can we learn about this? I promised you that we could do astronomy with this. How do we go from a bunch of wiggles to learning about the universe? Now this is really what I do. Is how do we go from these wiggles to learning about the source that made it? And the way we can do this is by virtue of knowing what a gravitational wave should look like. So here's a simulation of 2 merging black holes. You can see the black holes as these little blobs here. Down here is a representation of the curvature of space-time. As they orbit around each other, they emit gravitational waves, the signals at the bottom down here. These gravitational waves carry away energy and angular momentum, which shrinks the orbit. So it starts slowly. We'll skip ahead now to where they get closer. You see, as they get closer, it gets faster and faster. It's a runaway process. They plunge in and merge. They form a single bigger black hole that quietens down and forms a stable black hole at the end. So you get a pattern of gravitational waves here of a slow in spiral. Then we get the loudest burst as the 2 black holes come in and merge. And then we get this damping down, which we call the ring down. Very quiet.
You call the what?
Ring down. So each part of this signal encodes a little different bit. So here's our first gravitational wave signal in the way that we analyse it. So we've taken into account the sensitivity of our detectors. And you can see it starts quiet and we can't really resolve anything. That's where it's at low frequencies where we're not sensitive to it. As it gets closer and closer to each other, the signal gets louder, both by virtue of the gravitational wave itself becoming stronger as we have faster moving objects and stronger gravity, and also because these are frequencies which we are more sensitive to with our detectors. We have the merger and ring down here, and you can see it quietens down again. Now, the masses of the two black holes controls the form of this signal. So there's a particular combination of the two masses which we call the chirp mass, which controls how quickly we sweep through these frequencies. So if you were to listen to one of these, it makes a chirping sound. You might have listened to these. You have to be able to make that sound to join LIGO.
Are we gonna have a seminar? And they
Oh,
give
yeah.
it?
Is there going to be a quiz?
You can
So the new workshop we do to get people involved
Yeah.
in CIERA, it's gonna be the chirp workshop. We teach how to make gravitational wave noises.
Well, as long as that comes with, a bottle of scotch. I think we can work on that.
Sure, karaoke, that's
Yeah,
what it's gonna
sure.
be.
All right, now do a neutron, binary neutron star.
Yeah.
Those are much harder. So
Right.
the lower mass, the longer the chirp is. So a neutron star would be, and so on and so forth.
You have to
for
be
about
able to
a
do
minute.
circular breathing.
Yeah, right.
Okay, so the chirp mass controls the inspiral. So if we measure how rapidly we go through this phase here, we get the chirp mass.
How's the chirp mass related to the actual masses of the two black holes?
So it's a combination of the two masses.
It's like a weighted
It's
sum.
yeah, so it's a combination of the product of the two divided by the sum of the two to some fifth powers, basically. It's not particularly intuitive, but we measure it very well. What's perhaps a bit easier is the point at which we get the merger. So this is really set by the total mass of the binary, so just n1 plus n2. So if you measure that point, you get the total mass quite well. Now there's also the distance to the source. The distance controls the amplitude. The further away the signal is, the quieter it is. So you know how loud it should be for a given mass by looking at how loud it actually is. That tells you something about the distance. It's not quite as simple as that, because the orientation of the binary also determines how loud it is. So if you're looking down the binary, so the two black holes are going around that way, it's louder than if you're looking at it from the side. So there's a bit of uncertainty we get in the distance from adding that together. The time delay between...
Can I ask you a question about that, Christopher?
Yes.
Sorry, all this is a technical question, but you should be able to get the inclination from the ratio of the two polarizations. So why can't we?
Because we don't measure polarizations.
Yeah, you can't get polarization.
But we should be able to measure both states with LIGO. We can tell the ratio of the two polarizations from the
No,
measurement.
the LIGO nearly aligned, so we only basically...
Oh, because they're co-aligned. Right. Okay, thank you.
So you can measure the inclination
Yeah.
best, actually, if you're looking pretty much just down the edge, and you have the orbit wobble a bit because the black
Yeah.
holes are spinning.
Yeah.
And then you tell the difference between looking slightly this way and slightly that way is significant, so you can split that way. But we've not seen anything like that yet.
Thank you. Perfect.
So the time delay between arriving at the two locations tells you something about where it came from on the sky. If you hit Hanford before Livingston, you know you're on the Hanford side. Like that. And also the amplitude ratio, so the detectors aren't sensitive in all directions equally. It's kind of like a microphone. If you're immediately above, it's louder than if you're off to the side. So all these go to get the sort of location in space, how big are black holes, and figuring this out is the analysis I do. Now, unfortunately, what we are left with are plots like this. So I'm always very jealous of these people who do optical astronomy, and they have beautiful Hubble plots, which look at stars and so on. And this is what I have. This is. I still think this is beautiful.
You shouldn't be embarrassed by that. That's great.
So what we have here are probability distributions that we infer by fitting these models that we have for the signal against our data, and there's a bit of wiggle room because there's noise, so we're left with probability distributions. So these contours show that if we're inside this contour, there's a 50% probability, and inside this contour, there's a 90% probability of having the true source. So this is for our first detection. You can see it's quite a high mass source, so something 35, 40 times the mass of our sun. So we didn't know that black holes existed at this mass range before. We'd never seen a black hole of stellar origin that was this massive before. So straight off the bat, we discovered that our detectors work, which was pretty big. We made our first detection of gravitational waves. We found our first ever merging binary black hole system, and we discovered that black holes could be more than 20 times the mass of our sun, which we didn't know. So that's a huge number of discoveries immediately from this. So that was pretty cool. These, you will see that we have some other contours here. These are the other events that we saw during our first observing one. So we had LVT, it's LIGO Virgo trigger. We gave it that name because it wasn't quite as confident a detection. I think it will be renamed soon. But the anniversary of that is actually tomorrow. This is going to have some cake to celebrate. And this one here, the Boxing Day event, 15/12/26, it got nicknamed the Boxing Day event in collaboration, which I'm extremely surprised of because one, here in the United States, you don't have Boxing Day as a holiday. In Britain, it is a thing. Somehow the name stuck anyway. And what was more impressive is it was actually Christmas Day at the detectors at the time.
Oh, right.
But we named them based on Greenwich Mean Time, so it was Boxing
Maybe that's why it's Boxing Day too.
Yes.
Goes with Greenwich.
Yes, yeah. So these are the detectors. And you can see the masses are all quite different. So we have our heaviest first detection, the Boxing Day event, maybe down to 5 times the mass of our sun. And also something you might notice is the shape of these probability distributions is quite different. And that comes from this different shapes of the signals you see. So here are the different signals. Well, 15 and 14 is quite a short signal, just 0.2 seconds. And this is because it is a high mass source. High mass means it merges at low frequencies. We only get a short signal. So here we are. And because it's a short signal, we don't measure the in-spiral particularly well. We measure the merge and ring down quite nicely. That's why the probability distribution looks like a little blob, because we sort of get a mix of information about the chirp mass and the total mass. For the other ones, they're lower mass signals, they're longer signals. We measure the in-spiral really well, which means we measure the chirp mass really well. And those banana shapes you saw are basically lines of constant chirp mass. And we don't measure the total mass as well, because we basically can't tell anything about the merger and ring down because they're quite small, quiet features of the system.
So is the merger always at the peak of the waveform?
Yes.
That's what you
Yeah.
take to be the merger point?
Yes, well, that's the prediction from the model.
That's distance, so it's when they're colliding.
Yes, so that's where they come in together. They're so close that they stop orbiting, basically plunge in towards each other, form a single big black hole.
Boxing Day,
Yeah.
the mass was much smaller too.
Yes,
You're saying that correlates to the length of the reading, right?
yes. So the fact that it carries on going much longer, it merges at a higher frequency, so the chirp goes up.
But its noise isn't very.
Yeah.
So
So the amplitude is smaller. So the heavier you are, also the louder the signal is intrinsically. So in addition to being closer or further, so you need both the mass and the distance.
So that's why I guess I had a cool question, because LVT there looked like it was potentially the largest mass. I mean, I guess that long thing means that there's some question
Absolutely.
on what the reliability, I guess, of that signal, right? Which you mentioned. You said it's
Yeah, so we're very uncertain of it because it's quite quiet. So this is why we have such a big uncertainty, because since it's quiet, it's much harder to accurately get the parameters.
So based on those kind of conclusions, do you think that the mass is actually smaller than maybe what that perceived?
So we're pretty confident in this. So I'll skip ahead now.
Yeah.
So this plot includes all the signals I can tell you about.
So there's more.
I'm not saying anything.
You didn't say any of that.
Yeah.
We're analyzing our data, and when we discover something, we'll tell you.
So this is now including events from our second observing one. So we have 170104, which is my favourite because I led the analysis of this event. This was our first detection of our second observing one, and you see it nicely fits in sort of between the masses of the events we've seen so far. After that, we had 170608, happened in June. This is probably the lowest mass binary we've seen. It might be that boxing day event is low mass, and that's consistent, but it's probably this one. Again, this is a very low mass signal. Lots of in-spiral. We measured the chirp mass quite nicely because we have all this in-spiral. Don't know too much about the total mass.
And 0608 analysis was led by Eve Chase, who's a graduate student from
Yes.
Northwestern.
And this was a very tricky event to analyse because this actually happened when we were doing maintenance on one of the instruments. So we have to align the mirrors, and to align the mirrors, we wiggle them around basically. And as you can imagine, having the mirrors being wiggled around is not what you want when you're trying to accurately measure the distance between them. Luckily, it was happening right at the end, and so it only disturbed part of the signal. So we had to do some careful analysis of, okay, we can ignore all that stuff and do all this stuff. So it was really tricky for the team to do that. I was not jealous of that. And so rounding out the events from 02 is 1708-14. This was the first detection we made, including Virgo. So Virgo came on in August. 2 weeks into August, we made this detection of the 3. So, okay, some of the high mass.
I have a quick question.
Sure.
So it looks to me like the 2 at the top and the 2 at the bottom are very similarly shaped. Could it be that you're detecting something from the same event, just a wave later or before?
That has been suggested. It's probably not. So the similar shape is really just because these signals always look kind of the same. So we have these these shapes here where you get them measure both the in-spiral and a bit of the merger, so you get constraint to this region.
But it would be possible to cause more than one ripple with the same event, so you could detect the same event with more than one.
So, well,
Sure.
it's possible in the event that you have something called gravitational lensing. So this is where you have something really massive between you and the source. And it's massive, so it bends space and time. And so you can be bent into multiple images. So you have one signal going around one side, it arrives a bit earlier, one going around the other, and it arrives later. And so people have suggested this. The probability of that happening is really small.
Well, you're
And
talking
it-
a 2-year difference.
And the
also.
time, the time difference would be what?
So it depends on the source of the size of the lens. So this actually is the sort of scale you'd expect for lensing from a galaxy cluster.
Oh, is it really?
Well,
Okay.
yes,
Wow.
because 2 years with light time is not very far.
That's
apart.
true. When it comes to the universe, 2 years
The
really isn't that
calendar years
much.
is quite short.
The first to cover gravitational lens has a time delay of 470 days. So,
So therefore,
yeah.
Wow.
it's
So
not
that-
impossible.
So that's it's a really good idea. What you'd
So get
expect
ready
though,
for your next career.
Yeah, we have a graduate student opening there.
I am open to career shifts.
Rapid career shifts, keep that in mind.
Want to move back to Chicago, Zach?
You just have to capture my attention.
if they were lensed, what you would expect though is actually the masses to really quite closely overlap. So here they are quite distinct. There's not much probability of them being the same mass, so you would expect them to be close.
So it changed the arrival, but the signal in theory would be almost identical, which makes sense if it's the same event.
Yes, so
Right.
maybe not exactly the same,
But
but pretty much.
they'd be pretty on
So
top
you're
of each
saying
other.
they basically layer on top of each other?
Yes, basically. So not identical because the detector will be slightly different. There'll be some different noise around, but
Right.
basically the same. Okay, so this is what we have so far. Here's a nice graphic developed here at Northwestern, which shows in blue the black holes we've detected with LIGO and Virgo. You see we have 2 black holes becoming one big black hole. And the population in purple are all the black holes we knew about before LIGO and Virgo. These are from these X-ray binaries. And you can see these are lower mass because they form in a different way. They're different systems. So we're really filling in this picture of where all these black holes come from. Before gravitational waves, astronomy, we had no idea that the extended all the way up here. Now we do have an idea. And one of the things I'm particularly interested in doing is putting together the information from both the gravitational waves and the electromagnetic observations to figure out about the entire population, how these binaries form, how they evolve, the details of all the messy physics that goes into starting with 2 stars and getting them to live their lives, to come together to leave behind these remains. So we have a pretty good idea of the family of black holes out there. We know that they come in a range of sizes from the smallest up to 30 times the mass of our sun or so. But that's not all that is out there in terms of black holes. There are in fact much bigger black holes. So I have to be quite careful when I say that 150914 was the biggest black hole that we've seen to date. The biggest black hole in this regime where it could be the remains of a star, but it's not the biggest black hole by quite a long way. And that's because there are also supermassive black holes. So this is one of my favourite pictures. Here we have a nice galaxy which is blasting jets out of it, these massive bubbles being blown out. And these are powered by a black hole at the centre of this galaxy. Now we think that every galaxy has a supermassive black hole at its centre. And this includes our own galaxy. Here's a lovely video from the European Southern Observatory, which is a zoom into the centre of our galaxy. Yes. So here, starting out in optical, is the band of the Milky Way, and we're going to zoom in and get a picture of it is full of stars. As we go further, we start to get obscured by dust, so the images will switch from being optical light to being infrared. Keep zooming in to the very centre stars. And here we have actual footage over about 15 years of stars moving around in the centre of our galaxy. And if you look at these, you'll see that they wobble around on orbits. These orbits, if you trace them out, into a simulation, you can figure out that these stars are orbiting something. They are orbiting something which is about 4 million times the mass of our sun. About 4 million times the mass of our sun in a ridiculously small area, at which we can't really see anything being there. So the answer is the only solution to this is there needs to be a black hole, a supermassive black hole at the centre of our galaxy.
They would leave a mark.
So,
Oh, man.
if
2 weeks.
So this. If I was giving this talk about 3 years ago, I would say that this is the best evidence of the existence of black holes. In fact, the week after September 14th, I was giving a public talk on black holes, and at that time, of course, I couldn't tell anyone that we discovered black holes. So I was giving my standard talk, and I was showing this video and saying that this was the best evidence of the existence of black holes. And as I was saying it, I realised that that was no longer the case, and that was actually really when it hit me that we had made this detection, this discovery. But this is great. We know that we have these supermassive black holes out there, and what's more is that these supermassive black holes are potentially a gravitational wave source. Now, because they're so big, because they're so massive, we can't see them with LIGO, because big mass means low frequency. Low frequency is outside the range that LIGO can see. So here we have, as a function of frequency, the sensitivity of different gravitational wave patterns. So here is LIGO, and it's roughly sensitive to the same frequencies you can hear. So down to maybe a best of 10 hertz. Okay? And that's limited by the vibrations in the ground, basically. So you can't escape that on Earth. What we can do, as alluded to earlier, is go to space. And we have a space-based detector, which is LISA. And this is what I worked on during my PhD, and has a special place in my heart. Shane's smiling there, he's a big LISA guy as well.
This is what I do. And Christopher will come back someday.
So LISA is really a remarkable device. Instead of having these 4-kilometre long tubes on Earth, you put satellites in space. You don't need to build tubes now because space is a good vacuum. And what you have, in fact, is a triangle like this, which orbits around the sun, behind the Earth, cartwheels around, and you have this infront here. And I think this can really claim to be will be the largest experimental apparatus ever created, because these arms will be 2.5 million kilometres long. So just to give an idea of scale, the Earth has a radius of about 6,700 kilometres, The sun is about 700,000, 2.5 million. So it's ridiculously huge. But this is great because this will now give us sensitivity to the lower gravitational frequencies, which is perfect for these supermassive black holes. And in particular, we know that galaxies merge. Galaxies come together, they combine, they have a couple caught in the act, and as they merge, the black holes in their centres should fall together over time, come together and merge. And those signals, as you can imagine, you have millions of solar masses, are really loud. So with LISA, we will be able to see all of these basically in the mass range of around about million times the mass of our sun merging. We will be able to see all the way back as long as they happen in the universe. So by looking at these gravitational waves, we will get an idea of how these supermassive black holes form, how galaxies evolve by virtue of tracing out their black holes. And that's really good, because we're kind of in this embarrassing situation at the moment that we know that these huge black holes exist. We know they're millions to billions of times the mass of our sun, but we don't know where they come from. We don't know how they're made. That's kind of a big deal. That's pretty big. So this will help us figure out. Now, the thing I was particularly interested in during my PhD, and still working on a little bit now, are not where you have two supermassive black holes merging, but where you have one supermassive black hole and one regular stellar mass black hole. So this is the remains of a star from this cluster of stars surrounding it, and it comes together and orbits around. I'm not showing to scale here. This is called an extreme mass ratio inspiral. So the mass ratio is extreme, and we get a nice inspiral. Now, instead of a little chirp, which just comes together and finishes, these signals are much more complicated because, as a consequence of the extreme difference in masses, these inspirals go on for much longer. So what you end up with is something a bit more like this. It's a little animation made by my PhD supervisor. Up here, we have a plot of the little black hole orbiting around the big one. And you can see it zooms in, whirls around, zooms back out again, and the gravitational wave signal you produce at the bottom is much more complicated. You have a mix of frequencies. It's a really quite a big mess. And this, in fact, is quite a simple orbit. This is just going around in one plane. In general, you can be going up and down at the same time. So you have a big mix of different frequencies going on. And this will last for years. So potentially.
So every time it comes in and it's accelerated, it emits more energy and it's becoming more circular. In
Yes.
the end, is it purely circular before it merges?
Potentially, it will be more circular, but not necessarily completely circular. The amount of circularization is less efficient for these extreme mass ratio systems. So these are much more complicated. You don't have the same simplifications as you do for more equal mass cases.
Does it swallow? I mean, does it?
Yeah, in the end it'll be swallowed. And you'll get a very quiet emergence.
So you're saying before we don't know where the supermassive ones start. The other one we've said, okay, they start from dying out stars, they start from these areas. I mean, are there theories?
Yes, there are lots of theories.
I'm curious, it's like, okay, if everything seems to go up in scale, does that mean that they're really big stars that have died that we haven't, discovered yet because there really aren't any more of those that exist, but we've now created these galaxies as a result?
Yes, that's
We
one
have
of
two
the
graduate
ideas.
openings, Zach.
So yeah, that's one idea. You start with these supermassive stars that collapse downwards. There are other ideas of you start with just a regular, still very large star, and somehow that leaves behind, say, 100 solar mass black hole, and then you feed it relentlessly, and it grows upwards. You maybe have a cluster, and they come in and merge. You can feed them a bit by having other things plunge into them.
Sure.
So when you're doing math on basically the spirograph that's
Yes.
going up there, in theory, this black hole in the center should be drawing mass from the other one that's rotating it every time before it flings it out. Why are the circles nearly equal from each fling? Because shouldn't it be drawing closer each time if it's losing mass?
So it's not losing mass because it's a black hole, so there's nothing to be stripped off. If it was a star, then that would happen.
Okay.
And in fact, tidal disruption events where you get a star come in and split across is
That makes
an
more
interesting
sense.
thing to study. It should shrink slightly because it emits gravitational waves, but the amount of energy lost is very small because of the extreme mass
Because of
ratio.
the-
So
okay.
it should actually shrink. So I should say this one doesn't shrink because
So
we
that's
didn't-
why the spirals stay relatively.
Yeah,
But
so
it-
what actually happens is that outer point is slowly getting in closer and closer and closer.
Closer and closer.
Yeah,
Yeah.
so it's what Don said, it's becoming more circular.
But it has to do a
But-
lot of
Yeah.
those.
Yes.
Well, how many chirps, I mean, these individual chirps are then observable?
the whole thing will be observable.
Right, and I guess it's going to depend on the masses, on how far those chirps are apart, how long that goes on.
Exactly. It
and-
depends on the orbit parameters. It's
Right.
really quite
This is
complicated.
probably the hardest problem in LISA right now.
Is it?
Yeah, this is one of the hardest data analysis problems because this will go on for years. The entire duration of the mission, potentially you have this going on. But you won't just have one, and
You'll have, yeah.
potentially you will have thousands, all on top of each other.
They have to separate
So
them.
yeah, so you could fire that thing up and just have constant signals. Just...
Yeah, yeah, so we call that the confusion problem.
Right.
Gee, and I thought the
That's
data on
a new-
LIGO was tough to negotiate. That sounds like a nightmare.
Yeah, so LIGO, we wait for signals,
Yeah.
and then they're tough to negotiate, right? In LISA, we have signals, and we gotta separate them.
And so what's the current thinking on doing separation?
There are many approaches. So right now, we're doing two things. One is what we call a global analysis, which is you analyze them all together.
Right.
And the
right.
other is how to identify ones like this, subtract it out so you can work on it by itself and work on everything else by itself.
Okay.
And
Now, the
that's
global
subtraction
approaches are,
part.
so essentially you're going to fit like, thousands of,
Yeah.
of complex exponentials.
It's a
to-
giant Bayesian,
So-
10 million parameter fit.
Uh-huh.
Yeah.
Yeah.
So it won't just
Good luck with that.
Yeah, I was gonna say.
Well, so we've demonstrated that it should be possible.
Yeah,
It's all
yeah.
about the computing power.
Yeah.
And so the good news is that LISA is due for launch in 2034.
We'll have quantum computers by
right.
then. so-
2034?
Yes.
Yeah.
Is it going to be more than one launch? I mean, given how far apart the
No,
parts are?
it'll be one.
Okay.
One launch?
So, like, I can draw you pictures afterwards. So we're about 15 minutes over, Christopher. Do you want to tie off and then we'll let
Yes.
folks
Yeah,
in?
but it's-
And well, I'm happy to talk to any of you about Lisa more if you want to.
Yeah,
afterwards.
that's pretty cool.
Christopher too.
Okay, so, so
It'll be sooner than that, yeah.
Okay.
What's that?
The launch will be sooner than that.
Then 2054.
The 2034 launch
34.
date,
Yeah.
we're doing today, for that launch date, we're doing today what we should be doing in 2022.
Oh, so you're.
So it should
you
have-
think you're
we've already
accelerated by-
We think
Accelerating,
we've
yeah.
already accelerated, so we'll
So,
see.
yeah, we don't say that, we don't tell anybody that.
It's all about money, right?
Can I just ask one question quickly, and I'll just give you a hint. It was when we had the panel discussion, we talked about the last observations, and wasn't it a neutron star with a black hole? And we
It's
also...
two neutron stars.
Two neutron stars, and we were using gamma and looking at
The
gravitational
telescopes.
waves. And the bottom line is there was a huge anomaly when the signals arrived.
A 1.7 second delay.
Yeah, do
Yeah.
we now understand that?
If you
Well-
talk to Raf, she will tell you yes.
Okay.
There's a big argument.
And, but only to Raph.
Well, no, we're physicists, right? We argue.
Oh, yeah.
Well, right, can we come back to that in a second?
We can come back a way long time
Good
from
memory
now.
on
It's just
that.
been on my
Good
mind.
memory on that. I was wondering
Yeah.
Go for it, Christopher.
So let's wrap up here as we're. So if you remember, with the LIGO signals, we fit the templates, we get some uncertainty on the masses, we get these large bananas out. Because we can't measure the masses too well, maybe we're down to sort of 10% accuracy, which is pretty good, maybe percent or something like that. With these, because we observe them for so long, and because the signals are so complicated, we can get much more precise measurements. So a recent study we did, we made a population of mock extreme mass ratio signals for different astrophysical assumptions, and measured how well we can measure masses. So here we have 12 different astrophysical models. They're all pretty much about the same. Here we have the measurement accuracy of the masses, and these are fraction errors. And you can see we measure the masses to something like 1 part in a million, 1 part in 100,000. So we can really measure these astrophysical parameters to ridiculous precision. better than you could really want for any sensible purposes. So with extreme mass ratio intervals, we will be able to measure the population of these supermassive black holes, really map out the details of the space-time and revolutionize our understanding of the population here. So I've covered a lot of stuff. To recap, in case anyone didn't take that nap, gravitational waves are a new way to do astronomy. It's really awesome. We can see these things which would be invisible otherwise, or get a new insight into systems like black holes, which we knew about some of them before, but now we have a much better idea of the family. So far we've seen this family of stellar mass binary black holes. We're starting to be able to figure out the details of how these evolve, so the messy physics that goes into forming these binaries. In the future, we will be able to see the full family of black holes. We will see the supermassive ones as well as the stellar mass ones. Get an idea of exactly what's out there. And that's just the information from gravitational waves, and I didn't get time to talk about this, but we can do more by combining gravitational waves with electromagnetic oscillations. So I only talked about black holes here, as that's what I've worked most of my time on, but of course we also have made our first detection of a binary neutron star now. This is our first real gravitational wave multi-messenger signal. And by combining these information together, we really get a much more detailed picture. So, thank you very much.